Oh, hi, thank you. Good to see you again after such a long time. Uh, so I didn't show the slide of the people who did the previous work. So let me just show it really quickly, though, because otherwise they might be listening and they will get upset. So, the superconductivity part, which I didn't get to, and the Seebeck coefficient of the heavy fermion was done by Howie and Dumitru, and the IKS state and the strain additions to the heavy fermion were done by Jonah and Jabin. So I have to thank all of them, and of course my experimental collaborators. But then this thing on the fractional states was done mostly by Jabin, Jonah, especially on pentalayers, and also with if on TMDs and now pentalayers. And great thanks go to my old collaborators, not old, they're young. I mean, they're, they're middle age young. My long-term collaborators, Nicolas and Oscar, and Titus, and Xiaodong, and Quansheng, and Hongming. Okay, so how much do you think should I review of the introductory FCI? There's talks of FCI. Oh, where's my coffee? There's talks of FCI plenty in this, right? Everybody knows about fractional quantum Hall? Sigma XY, strata formula? Yeah. Very good, okay. This, similar? Everybody knows about this? Okay, similar. Okay, very good. How about this? Everybody knows about this? Wow, incredible. We all go to lunch now. How about this? Everybody knows about this? Haldane Chern Insulator, the Haldane model of Chern Insulator. Everybody knows. If people don't know about it, then then that's treated as a capital crime in Princeton. So everybody knows about fractional Chern Insulator. Okay, wow, excellent. New features, you don't have gaps that scale with B. You have, if the Chern number is greater than 1, you have different states, right? Xiaodong Long mentioned about this. Good or not? Oh, very good. Okay, so let's start with here, okay? So let me tell you how you, I'm sure probably Di Xiao, right, talked about this. How do you test if a state, so, fractional Chern insulators, originally, you have a flat band, you don't care where it's coming from. The new developments, are remarkable because I never thought it would be realized. Remarkable states, they realized it. Flat band with Chern numbers. Normally, exactly flat bands with Chern numbers is impossible. Exactly flat, if you want it exactly flat. You can get to like exponentially flat. Even that requires large, long-range hoppings, but exactly flat is impossible. And you want that plus strong interactions, plus you want to change the electron number. That, at the beginning, was thought impossible in 2011. So the FCIs were built on models. They were obviously very artificial. They were not continuum models. They were lattice models. And you had a flat band that was quasi-flat. You added an interaction that's larger than that bandwidth, but smaller than the gap. And you project into this flat band. And this flat band has a Chern number. And then you would find FCIs. And the one thing to remember is that in numerics on small sizes system, you'd find FCIs even on 12 sites, so 3 by 4 lattices. Okay, so very generic. You have a flat band with some Chern number. Most of the times, unless things go crazy, you can find FCIs even in very small sizes. And what does that actually mean? Because in small sizes, I can't compute. I can do I can do flux insertion really, but I can't really compute, at 3 by 4 sites, the smallest lattice you can find a clear FCI in for some models. It means that the state is really present there, it's really present consistently, and it means it's very easy to find. And we'll come back to the pentalayers on this because some of the the recent findings in pentalayers in theory of FCIs really just do that by biasing the system. But basically now what I wanted to show you is how do you hunt for FCIs. So this is a large system size, 6 by 4, 24 sites, 8 particles, so filling 1/3. And you take the interaction, and this is a projected interaction, so no kinetic energy, and you just diagonalize it, okay? And you diagonalize the interaction, and the key thing to find an FCI at filling 1/3 is the presence of these threefold degenerate states, okay? So you get these threefold degenerate states, which on the torus are the degeneracy of a Laughlin state, okay, filling 1/m, and you get them at the right momentas. And these are momentas that are really, compatible with Lieb-Mathe-Schulz theorem. I'm sure Masahi, I don't know what he talked about, but I think he talked about some of these things. Okay, so they are compatible with basically no-go theorems. You can find them in other ways. So at the beginning, you can just, we didn't know about this because it was found afterwards. But what we did is to just have a folding of the fractional quantum Hall torus and momenta onto the FCI lattice. And here you can match more than just the ground state momentas, which would be just Lieb-Mathe-Schulz basically for these cases. But you can match, for example, the quasi-Hall momentas, which is a further check. So what you do here, for example, this thing here is you take out one particle. So you say you stay at 6 or 2 particles, whatever. You stay at 6 times 4, 24 sites, but you lower the filling, okay? So you have, for example, 7 particles. That's 7, that's lower filling at 1/3. So, you added some holes in the system. And then there's, in fractional quantum Hall, there's these things called Haldane pseudopotentials, which are Hamiltonians for which the quantum Hall states, the fractional quantum Hall states are exact. And not only they are exact, but their quasi-Hall states are exact. The quasi-particle states are not exact, but we won't get to that. But the quasi-Hall states are exact. And you can find their counting, and their counting is basically given by some fractional statistics. Counting is basically some Haldane statistics. Of course, we don't have the pseudopotential Hamiltonian here. We're just diagonalizing some, Hubbard Hamiltonian repulsive in a Chern band. So we're not going to expect exact degeneracy. There was a question? Yes.
How can you set a state with specific momentum when strong interactions are present?
As many-body momentum. I can always take a state and translate it by, one unit cell. And it's not just single particle states. I just translate the entire, I have many-body states are just sums of Slater of non-interacting states with different coefficients. Those have to respect translation symmetry because the initial Hamiltonian was translation symmetric. So it's a many-body translation momentum. It's not a single particle translation momentum, but you can do the same. Okay? It's a symmetry. So whether you apply it on a single particle sector or a many-body sector, it's still a symmetry. So it's just the eigenvalue of the translation operator. I can put them in those momentum sectors. Very good. More questions? Okay. So basically here, the other thing that you can do is, of course, as I said, add quasi-Halls to the system. And you can see that in this, for example, for the same band, now you have a clear separation of a low energy manifold of states from a high energy manifold of states with a clear gap, right? You can see the gap here. These states are not degenerate because this Hamiltonian is not a Haldane pseudopotential. So it's not even these states are not degenerate. You can see 2 of them are degenerate by inversion symmetry, this and this. But the other one at 0 momentum is a little bit split. This is what would happen, for example, if you did Coulomb interactions in a fractional quantum Hall state. You'd get split degeneracy. Of course, as you go to larger sizes, the split degeneracy should become exact degeneracy exponentially. But unless you do the Haldane pseudopotential, so this particular Hamiltonian for which the fractional quantum Hall state is exact, you'd see some splitting. You see the same thing here. You see some splitting. In the quasi-Hall, you see some splitting. But if you look per momentum sector, below this gap, you'll find out the exact same counting as that of the fractional quantum Hall state, plus some folding to, the Briand zone is not exactly the same in the 2 cases. The fractional quantum Hall has a different Briand zone given by the number of fluxes. This is a Briand zone given by, this number of many-body Briand zone given by the size of the lattice. So you need to do some folding, but you would get you can match, and this was done countless amount of times in the original 2011 started field, that basically you can match the counting of the states below this gap to the one in the fractional quantum Hall state. So then you know that you have even further proof that this is a fractional quantum Hall or FCI state, fractional Chern insulator. It's a zero field. Why isn't this enough? Well, this is not enough because I could have a charge density wave, and that would have it, threefold degenerative, the right momentum charge density wave would give me similar threefold degeneracy. But a charge density wave would have some structure in momentum space, for example, in the occupation number. So the other thing you can do, and would have different quasi-holes, actually. So you do this, then you plot the occupation number in these many-body states, okay, in this many-body states, the occupation number of each momentum, of each single particle momentum. This is occupation number. This is just gamma dagger gamma, okay, in these many-body states. And for FCI states, or fractional Chern insulator states, or fractional quantum Hall states, this should be a featureless liquid, meaning every momentum should have the same occupation. Of course, on a finite size system, it's not going to happen because you're going to have fluctuations, but you don't want this to vary too much. And if you look here, this varies very little for the size of the system. You can clearly see that there's very little variation. For example, especially in this state, there's less than 10%, less than 5% variation actually in this number, around 1/3. Okay, so all these things are the way you hunt for fractional Chern insulator states in a system. And I think screen sharing has paused. I have this. So Princeton is pushing updates on computers like there's no tomorrow, every hour. That's probably because I've been neglecting it for a month. So now I'm paying for it. But basically, you need to do all these type of things. There's some other things you can do, entanglement. You need to do all these type of things to be sure that you have a fractional Chern insulator state. MOT2, Xiaodong probably, and Di Xiao explained. Mostly, I'll be focusing on this 3.7 degrees. FCI states, 2/3, 3/5. Okay? Zero field. You can see in zero field, there's still signal. They need a little bit of field to orient the domains. These are very low mobility samples compared to gallium arsenide. You see remarkable gaps. So it's really kind of an incredible thing. But then, if you want to dig further, so I'll tell you what, the purpose of this talk is to tell you what at least I think are the pitfalls and of doing theory and predicting states in these samples or explaining experiments, and then I'll go to pentalayers, especially since there's many angles involved in the sample. So these are the experiments on the 3.7-degree sample, okay? And they show the strata formula. 2/3, this is the filling 1, this is the Chern insulator, and this is the magnetization. This is the spin magnetization, okay? And you can see that the spin magnetization, and this is one of the most important things, because you can't have a Chern insulator without breaking time reversal, right? Now, breaking time reversal here, spin is equal to valley. There's only, you have a Chern number 1 per valley, as I think Di Xiao probably explained, one valley minus 1 in the other valley. The system, non-interacting system overall, keeps time reversal. But in order to get it filling 1, Chern 1 or minus 1, you need to polarize one valley. That's a symmetry broken state, quantum Hall ferromagnetism. And you can ask up to which filling will I still have spin polarized states? And the answer is in these diagrams from both Xiaodong and from Qinfei Mak and Jia Shen. They find a similar diagram. You see there's almost, you go non-magnetic around 0.3. So it's debatable whether 0.3, whether 1/3 filling is still magnetic or not. Certainly there's no FCI yet at 1/3 filling. And you go non-magnetic at 4/3. So these are all minus because you're all filling holes. So at minus 4/3, so after the filling 1, -1 Chern insulator, you're filling -1 with some Chern, you have spontaneous symmetry breaking. You lower your gate voltage further, you increase the hole density, you go to filling -4/3, the magnetization disappears. Okay? So this is kind of different than the quantum Hall states, the fractional quantum Hall states, the fractional Chern insulator. I mean, there's some similarity, there's some difference. You get the 2/3 state, but in a fractional quantum Hall state, you get a 1/3 state also. Okay, the Landau level is particle Hall symmetric too. These are not particle Hall symmetric. Certainly in terms of the magnetization, the 1/3 state seems to be demagnetized or very small magnetization. The 2/3 state, which is here, is magnetized, 2/3, okay? And it's got FCI. There's no FCI at 1/3. Very different from fractional quantum Hall. Xiao went through these models, right? I don't have to go through them. The McDonald models. You sure? Who wants me to go through them? Okay, very good. There's a silent majority, I think, that wants me to go through them. Silent majority represented by a vocal minority. They want, not that vocal. They want me to go through them. So basically, moral of the story, and this comes to the question that was asked here. These MOTE2, you've got MO, but TE in between. So the twisting, the first twisting, the interface is TE. So but the orbitals here in the single layer, so these are strongly spin orbit coupled systems. Okay, so single layer, which I don't have Moire, I just have, basically the band structure looks something like this. There's something, this is the K point, and the K point is spin up. The K point spin down is about, I don't know, 200 milli-electron volts below or 100 milli-electron volts below. So for Moire, for which I'm going to focus only on this, is spin up at K, spin down at -K. Valley is spin in this case. This is the Hamiltonian of taking two layers of this and putting them on top of each other and rotating them by an angle. So what does this represent? Well, that thing, and the reason why it's got a plus is because it's holes. If it had an electron, it would be minus, right? The gradient square term up to whatever, h bar, this is the IS, so h bar is equal to 1. So this thing represents just the quadratic dispersion. Okay? Is that clear? That's just the quadratic dispersion. And usually it comes out with minus this, but since it's holes, it's just the opposite. Right? So this, when I Fourier transform it, it will be -k². So you look exactly like this. Right? That's for the upper layer, that's for the lower layer. Now you have again a Moire-Briand zone caused by the K. You have valleys, right? So, but valleys spin here, so I don't have the extra degrees of freedom like in TBG. So I'm going to focus on one valley. Again, this Briand zone around one valley is small. They're decoupled. They won't talk to each other. I would need to hop 1/3 basically degrees, roughly 1/30 times to get from here to here. Perturbation theory would just kill me. Exponentially well good decoupling. So if I go in this model, I just have this k² from the upper layer, this k² from the lower layer. And if I just had the two-center approximation, like I argued in graphene, right, the upper layer would see a Moire potential, because the lower layer is twisted, of the lower layer, so it creates this thing. The upper layer is the interaction of the lower layer, vice versa. Okay, this was the off-diagonal term, right? This is just something at the Moire, modulated at the Moire. Everything here is modulated at the Moire scale because I now have the unit cell is the Briand zone is this, and the unit cell is 1/that. But now, and this comes to the two-center approximation I spoke before, you can notice these diagonal terms. This is V plus and this is V minus. They're just potentials in the upper and lower layer, okay? And these are not there in the two-center approximation. And really is because the hopping is through the TE anyways. So basically, everything here, V of R, is the sum of Fourier components at the Moire scale, of which you pick for most models at this angle, at this large angle, just the first Fourier component, i.e., this Moire-Briand zone has a reciprocal lattice vector, which is this guy from here to here, and the C3 symmetric ones, and this is just modulated at that reciprocal lattice vector. Okay? Is that clear? Questions about this? In this case, this is roughly the same order as this. To get these, you need relaxation, many things, etc. Okay, so moral of the story, you take this, it looks like a 2x2 Hamiltonian, but it's in the continuum per valley. So really what you need to do is expand it in a plane wave basis, but the plane wave basis is infinity. So you're going to get a continuum model with an infinite number of bands. But we're only interested in the first bands because you cannot, you need a lot of gates. Filling up the 1000th band basically is impossible because you reach breakdown fields. So you're only interested in the first bands. So, you can basically keep your number of plane waves to 12 or whatever, well, 36, and you get machine precision, good bands, twisted bands. You don't need to introduce, large plane wave bases, even the small plane wave bases. For people that took my class, this is obvious because actually I showed that graphene, the low bands are localized on the smaller plane waves, and similar things happen here. Just the same physics. Okay, it's the physics of a ramp-up term, a kinetic term, which ramps up. So the kinetic term is large at large momentas for large momentas, meaning large energies here, but its effect on the low energies is actually not that big because in perturbation theory it comes as 1 over. This is all the Moire physics. The first bands are always localized on the smaller plane waves. Questions?
I guess you can already flatten the bands with the in there, right?
This one.
Yeah.
So this, okay, so these ones are now parameters, different parameters. So this, so you, okay, so basically, this one you can't flatten, for example, right?
Yeah.
So what's the difference between these values? Well, and this is where I'm sure Dishao talked about it. Basically, these are different parameters obtained from different DFT calculations. So these T's and these V's here, this mass is just the mass of MOT2 K band single layer, 0.62 of the electron mass. Doesn't change very much when you twist it, same. These things here depend on relaxation, the way the lattice relaxes, etc. But around 3.8 degrees, you can sort of, if you do, a plane wave expansion of these potentials, you're going to have some coefficients. And those coefficients you can't get without DFT, without ab initio calculations. So, that's why, to actually compete in this field, well, unless you want to do just pure theory, which might not be related to the experiment, you need DFT. So basically, these potentials are given by 3 parameters, 2 first harmonic. Now, it was started originally by Allen, who actually invented these, seminal in inventing these fields, and these 3 parameters would be the only ones. But as Dishao showed, actually, these are much more complicated. There's some piezoelectric things that when you go to smaller angles, you're going to get a lot more parameters, which is next harmonics, etc., which change the bands dramatically. I won't get into that. But the moral of the story here is that different DFTs give you different parameters. Okay? So you can, different bands. For example, one of them gives you this band width, which is much larger than this. Okay? So to differentiate between the different parameters, the experiment should differentiate between them, but unfortunately, you don't have RPES on these things. You can't measure the band structure directly. They're 2D samples. A lot of them are encapsulated in both directions, so you really can't do. So, well, these ones are at least encapsulated in both directions. So how do we differentiate between the parameters? And the way to differentiate between the parameters is to do the many-body calculations and match the phase diagram. And there, what you find out is that the situation, so I'm going to give you the gist of the story in this because I want to go to pentalayers a little bit and show you how the situation is very dire in pentalayers in terms of theory. In this case, the moral of the story is that you cannot do projection just to a single band. So, in the Landau level story, the Landau levels were separated by a magnetic field. I could always crank up my magnetic field to be large enough so that the gap between different Landau levels was larger than the interactions. So then, by filling first Landau level, I could just project to the first Landau level because the interaction scale to the, could not hop me to the second band. Here, the bandwidth and the difference between the bands is, given, cannot be really tuned. Well, you can tune it with angle, but what the angle would do is just make it smaller. The angle will make it, so this is, kind of the first angle that you can actually tune the Fermi level, etc. So basically, you're kind of stuck with these type of difference between the bands and this type of dispersions. And for these, the moral of the story is that the band mixing, i.e. the influence of the interaction when the filling is in this band, the influence of this band is substantial and changes at least your numerics. So, or at least your physics. So anything that's predicted in this field, without taking into account band mixing, basically, needs to be checked once you add band mixing. And this is something that I'll exemplify right now. Okay, so as I said, does that make sense? So the moral of the story is here you cannot just do projection to one band. Band mixing that basically doesn't allow you to just project into this band. The Hilbert space cannot be just a projection into this. But I'll show you when I take the Hilbert. So you can take what you can do is, and going to pentalayers, there's still a gap between this band and this band, right? So this band, if my Fermi level is here, the interaction can populate this band, basically, but it can't populate it fully because that will be energetically disfavorable because there's a single particle gap. So what you can do is you can pick a Hilbert space made out of this band, which would be full projection, plus you can allow only a small number of particles in this band, right? Certainly there's not going to be, my Hilbert space, I put, 1/3 or 2/3 particles here, 2/3 number of sites. I will not be able, to transfer all of them into this band. So leaving this band full Hilbert space is not good. But, certainly there'll be, for example, a small percentage of the particles in this band in the many-body state, which you have to take into account, and it will change your physics. Very good. Okay, so this is what I meant. This is not Bicester McDonald, still Wu McDonald, Wu Hamiltonian, of basically first harmonic. Okay, as I said, Di Xiao showed that as you go to smaller angle, you cannot just take this Hamiltonian because the first harmonic is not enough. Smaller angle in order to do actual, theory that can reproduce the experiment or just theory, then one should take into account higher harmonics. But for this angle, for 3.89 to 4, first harmonic is okay, and you can see you only need these. You have the mass is given by single layer, let's say 0.6, 0.6, but these parameters, which are the 3 parameters which are enter here, and this is the intralayer potential, interlayer potential, they change a lot between different DFTs. Okay, these are different DFTs. Yeah? And this, I think, is Di Xiao's calculation. Okay, and so we did our own DFT. We agree with this one more, but that doesn't mean that the other ones are incorrect. They're just different potentials in DFT. So really, one should take these parameters and do a phase diagram. Let me show you the phase diagram of a single particle model. The single particle model has the following thing. You can again show, and I can't go through it because of lack of time, but you can again show that the first 2 bands have to be topological in this model. So there's no real, well, at least at some angle, so there's no real phase diagram in this model where the first 2 bands have Chern number 0 and 0, you can see. And given intralayer and interlayer potential, there's some, representation of the Chern numbers. For example, Chern number -1 and +1 for first and second here. Here, Chern number -1 and -1. So you can see the different parameters can have different Chern numbers. As you go to low angle, all the Chern numbers actually become the same. So it goes into the Landau level limit, but it's actually a different Landau level limit where the difference, the gap between the bands also goes lower. Okay, Berry curvature, quantum geometry. Have people gone through what quantum geometry is? in Berry curvature? Okay. They differ between different parameters. One of them is dloc is very, it's, you know, well, here you know, the projector doesn't show it, but here it's much more, here it's much more localized than in the other one. So basically all these parameters differ by several things. Now, what happens when you go to lower angle is that around 2 degrees, at very small angle, you're going to get 0 because you're going to turn back into the same. So forget about this one. But at around 2 degrees, you can see you get lambda level, Chern number 1, Chern number 1. If I will go to 2 degrees, this one will be Chern number 1, 2. So I get Landau level like structure, except, and this is from Di Xiao, but we confirmed it. So this gap between these bands becomes very small. Okay, so you can see it. You can see that it, you know, here 3.8 degrees, about 20. It goes to half of that. Okay, so it becomes very small. So band mixing becomes more and more important. Okay, so what's band mixing? Well, band mixing is the following thing. So remember how I told you at the beginning that at minus 4/3 filling factor, you see no magnetization, whereas at 2/3 you see magnetization. So 1/3, almost no magnetization, 2/3 magnetization, and FCI state, 4/3 no magnetization. And if I would just do one band projection, it would mean that I take the one band at filling, at one band from one valley and the other band from the other valley, and I just project into the first band. That's one band per valley projection. Okay? So if I do this, then when I would occupy, okay, when I go to filling 4/3, filling minus 4/3, meaning I occupy this one fully, and since it's one band per valley projection, I would need to occupy this one with minus, right? This with opposite spin by 1/3. So this one fully, this one 1/3 per one valley projection. This one should actually have lower spin, right? Because I occupy this and this, I lower the spin. So it would look like I'm doing the right thing, like 4/3 has lower spin than 1, right? But actually, that's not what happens. Well, that is what happens, but it's not spin 0. So here, 4/3 should have spin 0 in experiments. And actually, what we find in one band per valley, this is doing exact diagonalization on large sizes, is that you get similar magnetism with both sets of parameters as the 2/3 state at 4/3. So this is clearly not matching the experiment. Similar magnetism, right? So basically what happens, 2/3 would mean just this one occupied, these 4 states occupied here. So you'd have some magnetization. 4/3 is these band occupied in one band per valley, and this one occupied at 1/3. Okay? So there's several possibilities. You're going to get, there's a possibility of getting exactly the same magnetization at 4/3 as at 2/3, which is clearly in contrast to what the experiment tells you. Sorry? The idea is in continuum model. So we don't, so here, because the Berry curvature, at least in this case, is very spread out, we don't have any heavy fermion description, etc. So we do just continuum, it's just in momentum space. So you can see that one band per valley clearly cannot match it gives you the wrong physics with all the, it gives you 2/3 a spin gap, 4/3 a spin gap, spin polarized states, whereas 4/3 is clearly different. And then moral of the story, just to go faster, is that if you go to 2 bands per valley, so this means that you basically have lambda level mixing or band mixing. In other words, you can't just project into this band and this band, only the energetic. These bands are degenerate energetically, they're just in different valleys. You have to project, you have to take into account the next Hilbert space of single particle states and project your interaction to all of them, even though this is at a gap from it. If this gap was very large, I wouldn't need to take into account this, but you cannot match the physics and the gap is not very large. But if you take into account both of them, you can match the physics. So you can clearly see here, these are phase diagrams of interaction versus angle. The angle is around 3.8 degrees. But what you can see clearly here is that if you add 2 bands per valley, i.e. band mixing, the simplest thing, which is the matching the magnetization. Of course, we can match the FCI states, i.e. at fractional filling, we can get the degeneracy and match the FCI states. But the spin gap, or the spin states, you can see at -2/3 is fully spin, it's polarized. This spinful gap, i.e. if I have a spin gap, it's polarized, okay? At -1/3 is it's almost no spin, there's a little bit of spin polarization, but not much, but at -4/3 is again spin unpolarized. So this matches the experimental, at least spin polarization, which is the 0th order that one can do. And this immediately shows you that band mixing is important in these samples. Okay, so just wanted to put out the clear features. At small angle of MOT2, bands tend to be flat. This is due to folding from a quadratic band. This band, it's a bit different than graphene. Graphene has a lot more sensitivity on the angle. Graphene, the magic angle is really a magic angle. Here, there's no magic angle. There's, or as Dishao likes to put it, all angles are magical here. So basically, every time you go below 5 degrees, you're going to get a flat band. But what's different is, from Landau levels, is that the difference between the bands energetically is comparable to the interaction. And you do need, for anybody who's going to, who wants to do theory that can replicate the experiment, or at least predict new fancy states in the experiment that have a chance of being discovered. Well, sometimes the experiment has a chance of being discovered if you don't predict them. But in any case, you need to basically take into account band mixing. This is a similar conclusion that was obtained by Fu and Bergholz, and unpublished, I think, by Yang Zhang. And this basically gives you, for example, different things. For example, the composite Fermi liquid. So there's, at filling 1/2, there's a state called composite Fermi liquid. It's supposed to be gapless. And one of the ways you look at it, or one of the ways you characterize it, is by some degeneracy of the Fermi surface, at least in the fractional quantum Hall state. For example, these low degeneracies, for example, in the fractional quantum Hall state, you would have 12-fold degeneracy here. It's a Fermi liquid state, so this gap would go low. Okay, this is for Landau level. This gap would decrease as you increase sizes, but for finite size, you have the degeneracy. This is not the only way, and Adi Stern has another way of characterizing it, which could potentially be proved in numerics. But if you characterize it like this, you can do the calculations in MOT2 at filling 1/2, and you see similar things, i.e. you see this degeneracy, you see this twofold exact degeneracy here, which is, or almost exact. It's a little bit split here, but you can clearly see it. But this is one band per valley state. If we include band mixing, which I showed you is important for at least the magnetization, you can immediately see that this degeneracy disappears. That's not to say that the composite Fermi liquid state disappears, because the degeneracy is something, it's a gapless state, so it will disappear in the infinite limit anyways. But at least the way we identify states and the way people identify states now in the fractional Chern insulator composite Fermi liquid states should be done with band mixing, which changes the degeneracy of these low manifold dramatically. You can clearly see it here. Here you have different sizes, different degeneracies when you add band mixing. Okay, so how much more time do I have so I get to some 30 minutes. Wow. Any questions? Oh, thank you. Yes.
Theoretical understanding of why band mixing is important, or how does it stabilize FCIs by band mixing?
Well, it doesn't stabilize some of them. So it stabilizes some of them, but it doesn't stabilize. So theoretical understanding, so it's clear that band mixing should be important by just looking at the interaction scale and the difference between, right? Look at this band bottom compared to this one. Here it's even worse, right, for this set of parameters. But the band bottom compared to this one is smaller energy scale than the interaction. So it's clear the interaction is you can only project the interaction to one band if the single particle gap is larger than the interaction. Here it's the same order. So it's clear that there should, that there should be a band mixing effect. Now, how much that is, that's another question. And what that requires numerics, and numerics shows you that it's a lot. It changes. But it's clear that here you don't have the tuning of the Landau level. Right? I have some band mixing, I'm just going to increase my magnetic field and push the Landau levels more, right?
And also it has FCI, then for those models, single band would be appropriate.
But which depends what you mean by IC.
In energy scales.
Yeah, if this energy scale would be large, then you could just project into the first band. But then my point is that if you find a material that would have that, that wouldn't be very interesting either, because then you just go to Landau levels. We know what happens in Landau levels, right? What we want in FCIs is to find physics that's beyond Landau, well, ideally, right? In the end, right? I mean, well, people get greedy, right? What I, 11 years ago, I just wanted FCIs, right? Or 12 years ago. But now that we have FCIs that, Xiaodong, Kinpai, Jie, Long gave us FCIs, Allen, Liang, etc. A lot of the people that worked on it. Now we get greedier, right? Greed is what fuels our capitalistic society. So now we want something beyond the Landau level, right? And if I just have flat bands that are well separated, that's basically going to be Landau level physics almost, right? Because the Berry curvature is likely to be very localized, very unlocalized in that case too, because there's nothing close to other bands, so the Berry curvature has no reason why it to be localized. So that's going to be very much like Landau levels. So then maybe it's not so, well, it could be interesting in terms of, I'm not sure if something presented these data on superconductivity. Could be interesting in terms of inducing superconductivity because you don't have a magnetic field, so you can probably induce superconductivity much easier. But in terms of fractional states that you can get that are outside of the FQH, I think I'm happy with this paradigm when band mixing is important. It's a new detail. It's not a new detail. It's a new physics. There could be new states that are important. For example, the fractional topological insulator might be actually stabilized by adding some band mixing. Make sense? Yes.
Could you go to the slide where you show the quantum metric or the Berry curvature for the two models? Yeah. There's this trace condition or vortexability criterion, right? Couldn't you map the parameters with this as a constraint, or is it fulfilled for these both of these cases?
Yeah, I mean it's quasi-fulfilled. So that's a one-body criterion that basically makes the state like a Landau level, right? So it's roughly fulfilled. It's not that bad. The question is, so with the vortexability criterion, you could get exact states for a given Hamiltonian. Okay. Now the question is, the Hamiltonian in these samples, especially if you include band mixing, could be longer range, could be very different. So the vortexability criterion would give you, it's a single particle criterion that could become many body for a set of Hamiltonians. Okay, but we don't know what Hamiltonians we have here. So it certainly could be. My view is that the vortexability criterion is sufficient, could be sufficient, but not necessary. Also to get, we can get FCI states without having vortexability. So it could be sufficient and but not necessary. And again, if you go beyond that, could be interesting because it's not like the Landau level. So there's many perspectives that you can take. Very good. More questions? Everybody's waiting for the prizes. I feel they're not so good. I'm kidding. I haven't seen any of them. Well, nobody's getting any prizes if I don't finish. So, and I'm certainly not going to finish if I don't get any questions. The capability of lingering on forever. Okay, pentalayers. Long just showed this. Now, remarkably, what he also showed is that at least the 2/3 state and other states disappear. Right? This is unpublished data, which I think he showed here, disappear as you go to lower temperature. Now, let me explain to you why this is a completely different model, different system, which is so far, at least in my view, about, well, we understand what not to do, but what to do about zero understanding in this model. Okay, so here, Long explained that you basically have, you put pentalayers, so you have let me just, some moire, but first of all, at zero displacement field, you have this 5-fold vortex, right? K to the 5th, remember? Everybody remembers or not? Too long? You have a K to the 5th, K plus to the 5th, K minus to the 5th in the Hamiltonian. That's a n layer vortex. I showed in the TBG, I showed the 2-layer version of it, double vortex. You get more and more, right? You get this, because K to the 5th looks very flat. Then you add displacement field, and it becomes like this. You add moire. The problem is that this guy here, when you add moire, is very far away. You got 5 layers. So this guy here is very far away from the moire. Okay? This guy here stays away from the moire. Okay? That's the conduction band. So at the single particle level, this guy feels almost no moire. It has small gaps induced by the moire. The wave function basically with moire and without moire is so far away from the moire changes, at least with the Hamilton single particle Hamiltonians that we know, which might not be correct, by the way, changes by about 0.3% if you take moire and no moire. So very little. So hence the gaps that the moire will induce are very tiny, 0.1 milli-electron volts, the single particle gaps. So completely useless. Don't think about them. Also, they will give you the wrong Chern number. They will give you Chern number 5. Long C is Chern number 1 at filling 1 of the moire. So think of this as a gapless system. This is without moire unit cell. This is a gapless system of some flattish band and some potential. Now go to every valley. So here is graphene. So you have valley and spin. But let's polarize in spin and polarize in valley. Now I just have one of these bands. That's gapless band. The moire is not strong enough to introduce what it did in the, remember, in the MOT2, right? You folded at the moire, but the moire was strong enough, twisted, to introduce gaps. And this gap was large. I mean, not as large as the interaction, but was 15 electron volts, etc. This gap here that the moire introduces, because the moire is far away, is 0.1 milli-electron volts, is negligible. Okay, so just think of it as well, gapless system. So now you can see why the physics is completely different in this case, and this is a completely new system than the Landau level, because you actually have a gapless band. This band, by the way, has Berry curvature here. You just can't, you know, it doesn't have a Chern number because it's not gapped. If I just exclude these tiny, tiny moire gaps, which just exclude them, it doesn't have a, you know, it's got Berry curvature. It doesn't have a Chern number. And actually, with field, with displacement field, starts looking like this. So you can see there's actually very tiny gaps here, single particle, neglect them, that, and this is the folded in the moire zone. This is in the graphene, original graphene zone, okay? This is continuum K, original graphene. This is folded to the moire lattice. But you don't have a gap, so there's no way to do single band projection here, even if you wanted to. So it's a very different situation from Landau levels. Questions? Yes?
But how can it have order without the experiment? You know, they have.
Oh, very good question. So you can have it by interactions, right? And there are several things you can do, okay, which are all important. The most important of which is the charge ordering scheme, which I don't have time to go into it, but it's very important in all these things so it can give you different answers. So let me show you what people do. This is the phase diagram. This is our calculation, but in Hartree-Fock, but the MIT group, the Harvard group, and Beijing group, Jianping Liu, etc., have Shankar Dasarma have similar phase diagrams. Okay, so what happens is that if you park your Fermi level, okay, at this, say you're sitting at this filling, okay? Filling 1, okay, of the Moire cell. Now, notice that the Moire effect here is very minimal. This looks like folded bands. There's really just me representing the lattice in a folded Moire-Briand zone that for those bands at single particle level doesn't really exist because the bands don't really fill the Moire. So it's just, you know, me doing just basically representing the initial large momentum translation symmetry, large translation symmetry in a very stupid way on the Moire lattice here. But if I do this and don't consider the interactions to create a background potential that or even if I consider it, I will basically and then do Hartree-Fock. We obtained, as everybody else, a gap. Okay, so the interactions can gap the band, even though the band was gapless. This is if so there's several. I can't get into the discussion of interaction schemes, but there's several interaction schemes. I'm not saying one is better than the other. What I'm saying is that qualitatively they give the same results, but quantitatively not. And as I'll differentiate very soon. But the moral of the story is that if I have a Fermi surface, any Fermi surface, and do Hartree-Fock, for example, I could get what's called the Wigner crystal, which I think Long talked about. So what I can do is I can just fold my lattice at some momentum. Here, there's a natural momentum, which is the Moire scale. It's not that natural if, you know, the wave functions don't feel the Moire. But let's say I do it and consider the Moire as a perturbation or some pinning potential. If you do this, the simple Hartree-Fock will always give you a gapped, you see, like Hartree-Fock just brought down this band and it gapped it from the others. This is at filling 1. Make sense? So what we did is we did this, and you get, this is just the charge spectrum, okay? This Hartree-Fock charge spectrum. So now you have a band that's gapped, that's at filling 1, okay? So now, some phase diagrams can give you the correct, so this is a phase diagram that's very similar between all these papers, the Harvard group, the Berkeley group, I think maybe Mike spoke about it, the MIT group, Beijing group, etc. group. It's very similar. You increase the field and you get to a Chern insulator state in Hartree-Fock. Okay, so this band has got some gap here. These Hartree-Fock gaps are actually very large, the charge gap. See, it's a huge 20 electron volt charge gap. Now, as Senthil clearly points out in his talks, there's no reason to trust Hartree-Fock in these systems. For example, Hartree-Fock, we know on a gallium arsenide samples, mistakes the transition to a Wigner crystal by orders of magnitude. Okay? So, you know, this is a calculation. Whether it's the correct calculation done by us or by others, it remains to be seen. And I'll show you that there are things that are extra to this. So this is the putative quantum Hall state Chern equals 1 quantum Hall state Chern insulator state that Long sees, at least in this Hartree-Fock. There's no reason to trust the Hartree-Fock, but whatever. So now what's the difference in the spectrum between no Moire and Moire? And there's two ways of taking the Moire into account. What you can take into account is the Moire just at the level of single particle, or the Moire at the level of single particle plus the background of the valence bands. There's many things in the literature that are going, you know, that I don't have time to go into details. Also, it would be like a 2-hour conversation of which scheme is better. They could both be correct. None of them could be correct. But the moral of the story is both schemes give you the same charge spectrum. But where they differ, and this is the anomalous Hall crystal, this other one is the Moire, Chern insulator, what they differ is the collective mode spectrum. One scheme, which is the Wigner crystal scheme, would have low energy phonon modes. This is the scheme that has no moire. So there's nothing to fix its density. So it has low energy modes, and these are the low energy modes. You can see them here. As I increase the moire at, a Wigner crystal exactly at no moire should have phonons, because you break in translational symmetry, continuous translational symmetry, you get phonons. These are the phonons. They're exactly at zero, this axis. There's other collective modes because you have a spin full. But then you increase the moire, and you see the phonons only gap a little bit. The moire is not very important. In the other scheme, they gap more. At the charge spectrum, they look the same. Now, understanding the FCIs, and this is where it gets really dicey. So what one can do is, okay, well, now I have this charge gap, okay, this Hartree-Fock band. They obtained at filling 1. It's got a Chern number 1. Now I can just say, oh, I'm going to keep this band rigid and filling to fractional filling 2/3. Now, I want to point out that, in my opinion, in the opinion of the people that did the calculations that I want to point out afterward, this is biasing the system. And it's clearly biasing the system because you're looking at the band that you obtained at filling 1, and you're taking it to be rigid, and you fractionally fill it, and projecting to that band. However, since you obtained at filling 1 from interactions, this gap is of the order of the interaction, okay? So the interaction and the gap are the same, and we go into the same band mixing problem that we had before. Moreover, if I was just to do the calculation without doing the Hartree-Fock, which is already, doing Hartree-Fock is already, it's Hartree-Fock, so I don't know if it's correct or not, but doing the calculation without Hartree-Fock, I would fill this band by 2/3 if I want to go to filling 2/3. Now notice that this band has a lot of low energy degrees of freedom. It's not separated from any other bands. So the Hartree-Fock separates that band, but if I was to do an unbiased calculation from the beginning, I have a lot of low energy degrees of freedom. So projecting to one band is not allowed. In fact, actually, you can see that you have 3 bands coming here. On this thing, on this axis, there's actually twofold degeneracy here. You cannot project to one band. You're going to have fluctuations to higher bands because the gapless system is very different from a Chern insulator system. Okay, so moral of the story. If I just project into the Hartree-Fock band, and then fractionally fill that band, Hartree-Fock band obtained a filling 1, and then fraction, this is kind of a rigid band picture. Then, of course, I go to filling 1/3. I'm just fraction filling a Chern insulator. I get threefold degeneracy, Chern insulator filling 1/3, Chern insulator filling 2, FCI, fractional Chern insulator filling 2/3. These threefold degeneracy is the same. You can clearly see for different sizes, the fractional Chern insulator filling 1/3 is actually stronger in some situations than this one, not seen in the experiments. And you say, okay, well, I declare victory. I can get my Chern insulator. But this is really just biasing the system because I told you at the beginning that on a small, for gapped bands, if I project into band, I can get Chern insulator in the original papers, even at 12 sites. Very stable state with some conditions, vortexability, et cetera, that were found out afterwards. But here, again, let me show you what happens if you don't project to the bands. Okay? So now, if you, instead of projecting to the Hartree-Fock band, and considering this a rigid band, and now fractionally filling it, which, by the way, neglects all the, I told you that this is the charge spectrum, so it neglects all the goldstones, neglects all the gapless degrees of freedom that actually exist, because I'm just projecting the charge band. Even this is not allowed because I have, the interaction is of the order of the gap because the gap was created by the interaction. There's many If I don't do this, if I instead do an actual calculation where I take this band here, fill it to 1/3, but also actually take these gapless bands around it. Okay, so because it's a gapless system, I have to project to the gapless bands around it. Okay, and I do this. Now the problem with doing this is you can't go to a large number of sites because you only have you have 3 bands, so your Hilbert space explodes. But if you do it on small sites, that would be enough to get an FCI if this band was gapped. Then you find out, you see, there's no threefold degeneracy. There's no threefold degeneracy, no FCI. So then, people can say, well, you're just, then there's an argument. The argument, oh, well, you don't have enough sizes to show the FCI here because you don't have large, large lattices. Either way, the argument is that single particle Hartree-Fock projection, in my view, is completely biasing the system towards FCI and should not be considered as a proof of FCI. Now let me show you what you can do very quickly. And this is the result of about 8 months of work by Jabin, Jonah, and Nicolas, and helped by Yves. So now basically what you can do is the following thing. The moral of the story is that you've got, gapless states. You've got a flat band plus these gapless states around it, okay? Doing full diagonalization in these bands, which would the least, so you got, Coulomb interaction, 30 milli-electron volts. You got 3 bands around 30 milli-electron volts. Doing exact diagonalization here, your Hilbert space just explodes immediately. You can't do it for more than 12 sites. In 12 sites, you don't see any FCI. So how can you go around this to actually show what happens if the FCI comes in? Well, what you can do is several things, okay? And these are new methods, new numerical methods that Jabin, Jonah, and Nicolas and Yves developed basically. That basically what you can do is orbital restrictions. So you allow this flat band, you allow the number of particles in this flat band to be any, i.e. if I fill 2/3, I can allow from 0 to 2/3 of the size of the system to sit in this band. But now these bands have some degeneracy points close to this band, okay? So then I can restrict the number of particles in these higher bands, okay? Because I know, for example, that at the gamma point, these bands sit at 90 milli-electron volts away from the flat band. There's no way a 30 or 20 milli-electron volt interaction is going to be able to scatter me here. So you can do Hilbert space restriction for the higher bands, and you can add more and more states in the higher bands and restrict the Hilbert space and see how the FCI develops as I add more states into the higher bands, and that corresponds to adding the fluctuations into the flat band. And what you can see, and I'll just give you the gist of it. Let me see where the gist of it is. Filling 1, filling. What you can see is the following. This 0, 0, this 0, 0 corresponds actually to full band projection. Let me just do 2/3. I just have one more slide, and I'm going to finish with this one more slide. I just have to make sure I didn't kill this slide. Okay, very good. Okay, so this 0, 0 just means projection into the Hartree-Fock band. This is exactly what was done that I said is biased. And of course, you can see these nice FCI states. But now you allow fluctuations into the next band. And this is how many particles you allow into the next band, second band, and third band. Okay? So you allow fluctuations in the first band. I allow one more particle to fluctuate in the second band. These are finite size calculations, right? And immediately the gap to these threefold states decreases. Now you allow 2 particles. See, the gap stays constant. These are very hard calculations. The Hilbert space, this is, we managed to go to 24 sites. Okay, so that's much larger than, that's twice. Think about exponential increase, right? Everything is e to the, not e to the second, but e to the, okay? So we managed to go to large sizes. And then, you allow one particle into the first fluctuating gapless band, And then you can see the gap, FCI gap decreasing. But then you allow a second particle, and you see the gap increasing a little bit. So you're like, OK, I'm going to get FCI. Then you allow the third particle, and it just collapses. Fourth particle collapses, OK? Just in the first band. It's even worse if you allow particles in the third band. By the way, the third band and the first band, the third band, the second band, and the first band are actually degenerate at points in the Brillouin zone. You add particles in the second band, which means this being 1, it collapses immediately. So we find no evidence, theoretically, of a state at filling 2/3. Now, we hope that, people like Mike or people doing DMRG can go to even larger sizes and hopefully find FCIs here if they really exist. Now, considering what long stock and considering what I'm about to say now, I think the situation may be much more complicated. The point is, if there were FCIs at 2/3, like the original long juice paper, that have a large gap, 400 millikelvin, whatever, those should be, in my view, readily seeable, right, in numerics. So if the FCI still remains, if, say, the MRG people, Mike, Parker, et cetera, can go to larger sizes, and they see that somehow, going to larger sizes, this gap, they would need to go to large, this is 24 size, they would need to go to, larger sizes in DMRG, and then hopefully you would see this gap doesn't collapse. I'm not optimistic, but because this is the data, this is the state of the art that you have now, and it collapses immediately. If they show it doesn't collapse, then we still have a problem because in the experiment, it's, it would seem to be, at least at these high temperatures, much more robust than the calculations would show it. So we still, I think, would, even in that case, need to consider some other pieces of physics, or at least maybe we don't understand the full physics. Now, a more plausible, based on this data, more plausible interpretation is that the 2/3 state is not stable, like Long showed in his new experimental data, and also maybe it's not stable and we're missing some part of the theory. But in any case, the results are that the 2/3 state collapses and there is no FCI in this system, at least theoretically. So I'm not making any for these sizes. Okay, so there's two caveats. I can't say what you'd get for larger than these sizes, but usually these sizes are enough, more than enough for all our previous FCI experience to create FCIs. They go away here. This is the data. We don't see anything. So we either the correlation length is much longer, or we're missing some piece of the physics, or this is a matching of the experiment that the 2/3 state disappears. So with that, there's much more to do here. So thank you.
You can leave at a time, maybe just one question.
Just one question. Wow. Maybe two questions.
Sure.
Okay, what do you think? Two questions?
Yes, sir.
Okay.
So adopting long juice experiment, in finite temperatures, it seems to be like half FCIs and 2/3 fillings, but as you go lower temperatures, FCIs dies. So can you calculate not in zero temperature, but like free energy for including temperatures and do exactly the same thing?
If I was God, I could. Just a mere mortal, I think it is very hard. It's clearly the FCI is somewhere there in the spectrum, because you can get it for, it might be, somewhere there in the spectrum. Just I don't know what's around it. This is a zero temperature calculation. Well, this is, you see, it's a gapless system. So you're calculating, at the end, you've got a gapless system. I don't know where the FCI is. If it still is stable, why it would be stable in a gapless system? I don't know. So it's not clear. Yeah, I think basically there's no way to do it. I mean, this is the state of the art in terms of what you can do for at least exact visualization. The MRG might be able to do further, but for exactization, this is right now the state of the art. So it's very hard to go further. But what the state of the art does show is that all that we thought we knew so far about the theory in this collapses.
The gap topological state of your system, so then it should be driven towards this state with lower temperature. How do you understand from this picture of assuming that it's gapped that these observations are made?
Long's data is very puzzling. I have no explanation. That's why very puzzling. So I have no idea. I mean, the data is the data, right? So yeah. I mean, we don't even know if, right? I mean, and maybe we won't know the answer to this, right? Like a lot of his states disappear as you cool down, but some FCI states are still stable. But we can only cool down to whatever 10 millikelvin, right? I guess some people keep cool down further. Not. I don't know who actually. So we don't know if all states would disappear. There's a question of whether all states would disappear or only these ones. All the other states are much harder to get because they're higher denominators, so that's much harder in numerics to get. But the question is, would they all disappear? Who knows? So, or are some of them stable? And then we have, if they all disappear, then we at least know that the ground states are not FCIs. If some of them disappear, then it's even more puzzling, right? So this is really like, a really new system that's very different from anything we've known.
With the